Hello and welcome back. In a previous video, we discussed capacitors, and in that video, we discovered that the charge that builds up on a capacitor is directly proportional to the voltage applied to the capacitor and directly proportional to the capacitance of the capacitor. In a later video, we found that the energy that is stored inside a capacitor is equal to 1/2 times the square of the charge that builds up on the capacitor divided by its capacitance. In this video, I want to study how we analyze circuits that involve multiple capacitors. And the basic approach that we're going to use to analyzing these types of circuits is very similar to the approach that we use to analyzing circuits that involve multiple resistors. In other words, I want to come up with a way to describe capacitors that are in series or capacitors that are in parallel as being equivalent to a single equivalent capacitor. So first, looking at capacitors that are in series. Now, we're going to take a very analogous approach to what we use to analyzing resistors. So if you recall how we derived the equivalent resistance for resistors that are in series, what we said was that when resistors are in series, the current that flows through the first resistor will be equal to the current that flows through the second resistor. We also said that the total voltage across the two resistors is equal to the voltage across the first resistor plus the voltage across the second resistor. Similarly, if we look at capacitors, it turns out that the charge that is on two capacitors that are in series are going to be equal. And the reason for this is that if I imagine I had two capacitors that are in series like this, and I didn't have a battery down here, well, initially these capacitors are all going to be neutral. They're not going to have any charge on them. And when I insert a battery into this, what's going to happen is that electrons on this plate are going to move through this wire and are going to start building up on this plate of this capacitor over here. And what that means is that the positive charge on this plate of the capacitor on the left is going to equal the negative charge of this other capacitor over here on the right. Likewise, because the plates of a capacitor are so close together, when positive charge builds up on this plate, electrons are going to be attracted to this plate of the capacitor. So electrons are going to move from this capacitor over here and build up on this plate of the capacitor over on the left. And what that means is that the total charge that builds up on the capacitor on the left will be equal to the total charge that builds up in the capacitor on the right. So it's that basic idea that whenever charge moves from one place to the other, the total charge is conserved. So if you have a positive charge building up on one object, that has to go hand in hand with an equal negative charge building up on the other object. Now, since I want to describe these two capacitors with a single equivalent capacitor, the total voltage across these two capacitors is going to be equal to this equivalent voltage across the single capacitor. And the total voltage across these two capacitors is equal to the voltage across the first capacitor plus the voltage across the second capacitor. So let me call this first capacitor C1 and the second capacitor C2, and the voltage across the first one V1 and V2. So the total voltage across this whole thing is equal to V1 plus V2. And remember, the voltage across a capacitor is going to be equal to Q divided by C. So the voltage across capacitor 1 is Q divided by C1. The voltage across capacitor 2 is Q divided by C2. And since the charge on these two capacitors are equal, I can factor out this charge, and I can write this as Q times 1 over C1 plus 1 over C2. Now, if I compare the total voltage across the two capacitors in series with the voltage across a single capacitor, I can see that the two capacitors in series behave like a single capacitor with an equivalent capacitance that's given by this formula here. 1 over CEQ is equal to 1 over C1 plus 1 over C2. Notice that this formula is identical to the formula for the equivalent resistance of resistors that are in parallel. So what this means is that capacitors that are in series behave the same as resistors that are in parallel. Now, if I have several capacitors that are all connected in series, then the formula for the equivalent capacitance is very similar. It's going to be 1 divided by the equivalent capacitance is equal to 1 divided by C1 plus 1 divided by C2, and so on. So 1 plus C3 plus 1 divided by C4, and so on. Now, if I have capacitors that are in parallel, this is just like the resistors. So the voltage drop across these two capacitors is going to be the same. However, the total charge that builds up on the left side here is going to be equal to the charge that builds up on capacitor 1 plus the charge that builds up on capacitor 2. So the idea is that the total charge that builds up on these two things is equal to the sum of the charges that build up on the two capacitors. So we have that the equivalent charge that builds up on this is going to be equal to the charge that builds up on capacitor 1 plus the charge that builds up on capacitor 2. And recall the charge that builds up on a capacitor is equal to the voltage across the capacitor times its capacitance. So Q1 is going to be VC1 and Q2 is going to be VC2. And since the voltage across these two capacitors are the same, we can factor out this voltage, and I can write this as V times C1 plus C2. Now if I compare this formula with the formula for the charge across a single capacitor, which is given by V times C, I can see that these two capacitors in parallel behave like a single capacitor with a capacitance that's given by the sum of these two capacitors. So in other words, we once again see that capacitors that are in parallel behave just like resistors that are in series. That equivalent capacitance formula here, that CEQ is equal to the sum of these capacitors, that's just like the formula for the equivalent resistance of resistors when they're in series. So this is actually really nice because when we're dealing with these equivalent capacitance formulas, they're all the same formulas that you already know. You just have to flip this. So if the capacitors are in series, they're acting like resistors that are in parallel. And if the capacitors are in parallel, then they act like resistors that are in series. Now if I have multiple resistors that are in parallel, then the equivalent capacitance is going to be equal to C1 plus C2 plus C3 and so on. So let's take a look at a couple of examples. The first example says, suppose we have two capacitors that are in parallel. Show that the sum of the energy stored on the two capacitors is equal to the energy that would be stored on a single equivalent capacitor. In other words, show that the energy stored on capacitor 1 plus the energy stored on capacitor 2 is equal to the energy that would be stored on the equivalent capacitor. So I think I'm going to need a little bit of room on this, so let me go ahead and open up a blank sheet. So in this example, we're asked to show that the total energy that's stored on these two capacitors that are in parallel is going to be equal to the energy that would be stored on an equivalent capacitor. So remember that the energy that's stored on a capacitor, there's a whole lot of different formulas we have for this. One of them is that the energy is equal to Q squared divided by 2C. In fact, that's the formula I wrote down at the beginning of this video. So the total energy that's going to be stored on the two capacitors is going to be equal to the energy stored on the first capacitor plus the energy that's stored on the second capacitor. If I plug that formula into here, we're going to have it's going to be equal to Q1 squared divided by 2C1 plus Q2 squared divided by 2C2. And one of the things I want to point out about this formula is that we actually can't use this formula to solve this problem because the charges that build up on these two capacitors will be different. So for example, if capacitor 1 has a very large capacitance, then Q1 will be very large. If capacitor 1 has a very small capacitance, then the charge that builds up on capacitor 1 will be very small. The thing that the two capacitors have in common is not the charge that builds up on them, but the voltage difference across them. And in fact, that's also going to be shared with the equivalent capacitor. The voltage across the equivalent capacitor will also be equal to V. So what I want to do is I want to find the formula for the energy that is written in terms of capacitance and voltage. And when we can do that is remember that the charge that builds up on a capacitor is equal to the voltage times the capacitance. So if I plug that into here, I can see that the total energy is going to be equal to V times C1 quantity squared divided by 2 times capacitance 1. The energy stored on capacitor 2 will be equal to V times C2 quantity squared divided by 2 times capacitance 2. If I simplify that a little, this is equal to 1/2 V squared C1 plus 1/2 V squared C2. Now, since the voltages across the capacitors are the same, I can factor out the 1/2 V squared term, and I see that the total energy stored in the two capacitors is equal to 1/2 V squared times the quantity C1 plus C2. And the final step in solving this problem is realizing that for capacitors that are connected in parallel, the equivalent capacitance is equal to C1 plus C2. So the total energy that's stored in the two capacitors that are connected in parallel is in fact equal to 1/2 V squared times the equivalent capacitance. And this is the formula we would have gotten had we just calculated the energy that was stored on the equivalent capacitor from the beginning. So the last example that I want to look at says a 7 microfarad and 3 microfarad capacitor are connected in series by a 24 volt battery. The question asks us to determine the amount of charge that builds up on the plates of these two capacitors. So the basic idea behind this is that all we need to do is find the equivalent capacitance for these two capacitors that are connected in series, and then we can use the formula that we normally use for the charge that builds up on a capacitor, which remember is just equal to V times C. Now remember that the equivalent capacitance that builds up on the capacitors, this is the same type of formula for the equivalent resistance when resistors are in parallel. And remember that if we just have two of these things, then the formula is equal to the product of the two capacitors divided by the sum of the two capacitors. So that's the same type of formula I used to use for resistors that are in parallel. So if I plug this in here, we have 7 microfarads times 3 microfarads divided by the sum, which is going to be 10 microfarads. And if I plug that into a calculator, I can see that that's going to be equal to 2.1 microfarad. So the total charge that builds up on this is going to be equal to 24 volts times 2.1 microfarads. And if I plug that into a calculator, I can see that that's equal to 50.4 microcoulombs. So that's the charge that'll build up on these capacitor plates when the capacitors are in series. And so I think this will be the last example that I look at, and this will pretty much wrap up our discussion of circuits. So this will be the last lecture we have before the next test, which will cover all of the electrostatics, so Coulomb's law, electric fields, potential energy, voltage, as well as all of the stuff that we've covered about circuits. And in the next video, I'll begin talking about magnetic fields.